All right, so this video, well, actually the next series of videos is going to be on, I guess, lean manufacturing in Six Sigma, specifically the math involved in it. And the math isn't that bad. It's just a bunch of terms mostly, but the math itself is not bad at all. It's all algebra. Okay, so first of all, what is Six Sigma? So I'm gonna use an example to answer that. So let's say you're in a manufacturing company and your job is to cut, is to cut this beam of metal into a smaller piece of metal and use like a saw or something, I don't know. So you cut it into that piece of metal. Cool. Well, no two pieces of metal are gonna have the same length. So let's say you measure the length after you cut it each time, and then you make a plot of it. So your first length is, let's say it's that long. Second length, pretty close. Third length, pretty close. Fourth length, oh, maybe it's way up there. Maybe you accidentally made a mistake. Fifth length, around there, and so on, right? You got like a distribution of data points for the different lengths of the beam that you cut. Cool. So what are some characteristics about this distribution? That sounded very fancy, but effectively you got a mean. So you have a X bar. That's a mean. That's a term that they use in lean manufacturing. X bar is a mean. And then you've also got standard deviation. Let's say that is your negative standard deviation, and that's your positive standard deviation. Cool. So you got those three things. So what is Six Sigma? Well, sigma is standard deviation. So what do they mean when they say Six Sigma? So, all right. Effectively on this drawing, the standard deviation would look something like that. But I'm gonna redraw it so it's not like sideways. So let's say that's your standard deviation. Cool. And this would be length of beam, I guess. And you had your average right there, X bar, and you had the standard deviations. So Six Sigma means that X bar is 6 standard deviations away from the upper or lower control limit, ideally both. So let's draw the upper and lower control limits. And these are just set by, I don't know, they're like the tolerances that you can have. So the upper control limit, let's say it's right there. Lower control limit, let's say it's right there. LCL, UCL. And then, cool. So ideally, this distance and that distance are each 6 standard deviations. And the standard deviation is defined by your distribution. So what are some things that could affect this? Well, if your I'll draw a new graph actually. So you got your lower, you got your upper. Let's say instead of your X bar being in the middle of the UCL and LCL, let's say your let's say your distribution is like over here. So it's more towards the left. And now maybe you have like 2 standard deviations here, and you have the remaining 10 standard deviations over here. That is not good. But we'll cover that with CP and CPK, I think, in the next video. But this video, just going over the concepts. So if the standard deviation isn't in the middle, or if X bar isn't in the middle, you'll end up with less than 6 standard deviations on both sides. On one side, you have 10, which is great, but on the other side, you have 2, which is not great. Another thing that could go wrong with this is, you got your limits. Let's say your distribution is huge. Let's say it's huge. So you got your X bar, and then you got, let's say a standard deviation is like, I don't know, let's say it's like that big. It's a good way to draw that. I guess like that. Standard deviation. So maybe in this case, the lengths aren't equal. I know that. I'm just drawing it as an example. Let's say in this case, you've only got 2 standard deviations on either side of the mean to the upper and lower control limits. Then this would not be 6 sigma as well. So 6 sigma means that you have at least, well, the goal is you have 6 standard deviations on both sides of X bar of the mean to the upper and lower control limit. So if you have that, that's really good. That's the whole idea of 6 sigma. And next video will be CP and CPK, which quantifies how close you are, or how off-center you are, and how wide your distribution is. So that's the whole goal of CP and CPK. But that's the concept of 6 sigma. So again, you're doing a manufacturing process. No 2 lengths are going to be perfectly equal. So you plot them over time. You find X bar, which is a mean. You get the standard deviation, which you could just do in Excel. And then you see how many standard deviations you are away from that UCL and LCL. If you're 6 or more on both sides, that's great. If you're less, that's suboptimal. Cool.